When you toss a ball into the air, you give it kinetic energy. This kinetic energy transforms into potential energy as the ball rises, and then back to kinetic energy as the balls fall. What happens to the energy when you catch the ball? I would answer that question in today's video. The topic is conservation of energy.
Conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed. Energy can only be converted from one form to another or transferred from one place to another. Energy transformations. Mechanical energy transformations. Bicycles, roller coasters, and swings can often be described in terms of mechanical energy. Mechanical energy is the sum of kinetic energy and potential energy of the objects in a system. Mechanical energy and total energy are not the same because there are types of energy that are not mechanical energy. As a result, mechanical energy is not necessarily conserved. However, the mechanical energy of a system often remains constant or nearly constant. When this is the case, energy is only transformed between different kinds of mechanical energy. Falling objects. Look at the apple tree. An apple Earth system, which is a system that includes an apple and Earth, have gravitational potential energy. The apple Earth system does not have kinetic energy while the apple is hanging from the tree because the apple is not moving. However, when the apple falls, it gets closer to Earth, so the GPE of the apple Earth system decreases. This potential energy is transformed into kinetic energy as the apple's speed increases. If potential energy is being converted into kinetic energy, then the mechanical energy of the apple Earth system does not change as the apple falls. The potential energy that the apple Earth system loses is gained back as kinetic energy. The form of mechanical energy changes, but the total amount of mechanical energy remains the same. Projectile motion. Energy transformation also occurs during projectile motion, when an object moves in a curved path. Look at the picture and consider the ball Earth system. When the ball leaves the bat, that ball is moving fast, so the system's kinetic energy is relatively large. The ball's speed decreases as it rises, so the system's kinetic energy decreases. However, the system's gravitational potential energy increases as the ball goes higher. At the top of the ball's path, the system's GPE is larger and kinetic energy is smaller. Then, as the ball falls, the system GPE decreases as its kinetic energy increases. However, the mechanical energy of the ball Earth system remains constant as the ball rises and falls. Swings. The mechanical energy transformation for a swing are similar to the mechanical energy transformation for a roller coaster. The ride starts with a push, which transfers kinetic energy to the rider. As the swing rises, the rider loses speed but gains height. In energy terms, kinetic energy changes to GPE. At the top of the rider's path, GPE is at its greatest. Then, as the swing moves back downward, the gravitational potential energy changes back to kinetic energy. At the bottom of each swing, the kinetic energy is at its maximum and the GPE is at its minimum. As the rider swings back and forth, energy is continually transformed between kinetic energy and GPE. However, the rider swings less and less on each cycle, unless he or she pumps the swing or gets someone to provide a push. Other energy transformations. Consider the swing again. Think about what happens when you continue to swing without getting a push or pumping. The swing slows down and eventually comes to a stop. The mechanical energy of the swing Earth system decreases. At first, it might appear that that energy is being destroyed. However, recall that there are other forms of energy aside from mechanical energy. Energy transformations often involve these other forms. The effect of friction. If the mechanical energy of the swing Earth system decreases, then some of other forms of energy must increase by an equal amount to keep the total amount of energy the same. What could these other forms of energy be? Think about friction and air resistance. With every movement, the swing's ropes or chains rub on their hooks and air pushes on the rider. Friction and air resistance convert some of the mechanical energy into thermal energy. Thermal energy is the energy of heat and hot objects. With every pass of the swing, the temperature of the hooks and the air increases slightly. Mechanical energy is not destroyed. Instead, friction and air resistance transform mechanical energy into thermal energy. This thermal energy is soon transferred to the surrounding air. Transforming electrical energy. Energy transformations can also involve electrical energy. Think about all the electric devices that you use every day. Electric stoves and toasters transform electrical energy into thermal energy. Televisions transform electrical energy into radiant energy and sound energy. The electric motor in a washing machine transforms electrical energy into mechanical energy. Light bulbs transform electrical energy into radiant energy. Transforming chemical potential energy. Fuel stores energy in the form of chemical potential energy. For example, most cars run on gasoline, which has chemical potential energy. A car engine transforms this chemical potential energy into thermal energy and then into mechanical energy for the car's motion. A car engine also gets very hot when it's used. This is evidence that much of the thermal energy is never converted to mechanical energy. Power. How fast energy changes. Think again about the energy that your body extracts from food every day. You probably get enough energy from the food in one day to jump nearly 10 kilometers into the air. If this is true, then why can't you do this? You might have enough energy, but you don't have enough power. Power is the rate at which energy is converted. Power can be found using the following equation. Power equals energy divided by time. Power is measured in watts. 1 watt equals 1 joule per second. A 30 watts light bulb transfers 30 joules of electrical energy into radiant energy each second. A typical person can develop power of only about 500 watts for a jump. This results in a jump that is less than 1 meter high for a person with average mass. Let's make an example problem. Solve for power. You transform 950 joules of chemical energy into mechanical energy to push your sofa. If it took you 5 seconds to move the sofa, what was your power? So, we know that we need to find power. We already have energy transformed, is 950 joules. The time, 5 seconds. We use our equation, it is 190 watts. Let's check our answer. A typical human can develop power of 400 watts to 1000 watts for short periods of time. Developing a power of 190 watts will require some exertion, but would not be too difficult. The answer is reasonable.
I hope you found this video useful. Thanks for watching and until the next one, bye!